When astronomers first glimpsed beyond our own galaxy in the early 20th century, they discovered something that would fundamentally reshape our understanding of the cosmos. Galaxy clusters represent the largest gravitationally bound structures in the universe. Vast congregations where hundreds or thousands of galaxies dance together in an eternal cosmic ballet, bound by invisible forces we are only beginning to understand, holding within their immense volumes the majority of all matter that exists, the cosmic web and our place within it. As we begin our journey through the magnificent story of galaxy clusters, let us first understand where we find ourselves in this vast cosmic arrangement. Our home, the Milky Way galaxy, with its hundreds of billions of stars spiraling through space, might seem incomprehensibly large to us. Yet in the grand scheme of the universe's architecture, our galaxy is merely one modest member of what astronomers call the local group, a small gathering of galaxies that includes our nearest major neighbour, the Andromeda Galaxy, along with dozens of smaller dwarf galaxies that orbit around these two dominant spirals like cosmic satellites. The local group itself spans approximately 10 million light-years across, a distance so vast that light, the fastest thing in the universe, takes 10 million years to traverse it. Within this volume, gravity has drawn together these galaxies into a loose association, though calling it a cluster would be generous. The local group is more accurately described as a galaxy group, containing far fewer members than the massive clusters we'll explore throughout this journey. Our little gathering of galaxies contains perhaps 80 members in total, most of them tiny dwarf galaxies with only millions rather than billions of stars. Beyond our local group lies a much grander structure called the Virgo cluster, the nearest true galaxy cluster to our position in space. Located approximately 54 million light-years away in the constellation Virgo, this cluster contains well over 1,000 galaxies, possibly as many as 2,000, all held together by their mutual gravitational attraction. The Virgo cluster serves as the gravitational center of an even larger structure called the Virgo supercluster, also known as the local supercluster, which encompasses our local group, along with approximately 100 other galaxy groups and clusters spread across a region spanning 110 million light-years. The discovery that we exist within this hierarchical structure came gradually throughout the 20th century as astronomers mapped the positions and distances of galaxies across the sky. What emerged from these painstaking observations was a picture of the universe that resembles nothing so much as cosmic foam, with galaxies and galaxy clusters arranged along vast filaments and sheets that surround enormous voids containing very few galaxies at all. This cosmic web, as astronomers have come to call it, represents the largest scale structure of the universe, shaped by gravity acting over billions of years on the slight density variations present in the early universe. These filaments of the cosmic web stretch for hundreds of millions of light-years, connecting galaxy clusters like beads on an impossibly long string. Where multiple filaments intersect, we find the massive galaxy clusters that serve as the nodes of this cosmic network. The voids between these structures are not completely empty, but contain far fewer galaxies than the filaments and clusters, creating a Swiss cheese-like structure when viewed on the largest scales. Understanding our position within this cosmic web helps us appreciate the true scale and significance of galaxy clusters. We live in a relatively quiet corner of the universe, far from the dense centers of major clusters, where thousands of galaxies crowd together in volumes comparable to what our local group occupies with its mere 80 members. In the hearts of rich galaxy clusters, galaxies fly past each other at velocities of thousands of kilometers per second. Occasionally, colliding and merging in spectacular cosmic events that can last billions of years. The cosmic web itself emerged from the tiniest quantum fluctuations in the infant universe, variations in density so slight that they differed by only 1 part in 100,000. Yet these minute differences were enough for gravity to begin its patient work, pulling matter together over cosmic time to create the magnificent structures we observe today. Dark matter, that mysterious substance that makes up approximately 85% of all matter in the universe, played the dominant role in this structure formation, creating gravitational wells into which ordinary matter could fall and eventually form stars and galaxies. As we observe the cosmic web today, we're seeing the result of nearly 14 billion years of gravitational evolution. The process began when the universe was only a few 100,000 years old, when matter first became neutral and gravity could begin to dominate over radiation pressure. The first small clumps of matter grew larger as they attracted more material from their surroundings, eventually becoming dense enough for the first stars to ignite within them. These early structures continue to grow and merge, building up the galaxies and galaxy clusters we see throughout the universe today. The distribution of galaxy clusters throughout the cosmic web is far from random. Clusters tend to form at the intersections of cosmic filaments, where the density of matter is highest and gravity has had the most material to work with. These locations become gravitational attractors, drawing in more galaxies and matter from the surrounding filaments over billions of years. The largest clusters can contain thousands of galaxies and have total masses exceeding 1 quadrillion times the mass of our Sun, making them the most massive, gravitationally bound structures in the universe. Between the galaxy clusters, along the filaments of the cosmic web, we find smaller groups of galaxies and isolated galaxies making their way toward the nearest cluster. This ongoing process of hierarchical structure formation means that clusters continue to grow over time, accreting new galaxies from their surroundings and occasionally merging with other clusters in titanic collisions that release more energy than anything else in the universe since the Big Bang itself. The cosmic web also serves as a highway for galaxy migration. Galaxies don't simply sit still in space, but move along these cosmic filaments, drawn by gravity toward the massive clusters at the nodes. This movement can take billions of years, with galaxies slowly making their way through intergalactic space, sometimes joining smaller groups along the way before eventually falling into a major cluster. Our own local group is currently moving toward the Virgo cluster at approximately 300 kilometers per second, though we won't arrive there for many billions of years. The structure of the cosmic web has profound implications for galaxy evolution. Galaxies that find themselves in dense cluster environments experience very different evolutionary paths than those in less crowded regions of space. The high velocities, frequent interactions, and harsh environmental conditions within clusters can strip galaxies of their gas, quench their star formation, and transform their morphologies from beautiful spirals into featureless ellipticals. This environmental influence on galaxy evolution is one of the key ways that location within the cosmic web determines a galaxy's fate. Modern surveys of the universe have mapped millions of galaxies and their positions within the cosmic web, revealing its structure in unprecedented detail. Projects like the Sloan Digital Sky Survey have created three-dimensional maps showing how galaxies are distributed across billions of light years, confirming theoretical predictions about the web's structure, while also revealing surprising details about its complexity. These observations show that the cosmic web is not static but dynamic, with structures evolving and matter flowing along filaments in an endless cosmic dance. The cosmic web also influences the propagation of light and other radiation through the universe. As light from distant galaxies travels toward us, it must pass through the cosmic web, experiencing slight gravitational deflections as it passes near massive structures. This gravitational lensing effect allows astronomers to map the distribution of dark matter throughout the cosmic web, revealing the invisible scaffolding that underlies the visible structure of galaxies and clusters. Looking at the cosmic web from our position within it, we gain perspective on both our significance and insignificance in the grand scheme of things. Our local group, while containing trillions of stars and countless worlds, is just one small node in a vast network that extends throughout the observable universe. Yet we are part of this magnificent structure, made from the same matter that forms galaxy clusters, shaped by the same forces that built the cosmic web over billions of years. The birth of the first galaxy clusters. To understand how galaxy clusters came to exist, we must journey back to the earliest epochs of cosmic history, to a time when the universe was vastly different from what we observe today. In those primordial moments following the Big Bang, the cosmos was a hot, dense soup of fundamental particles and radiation, far too energetic for any structures to form. The universe had to cool and expand for hundreds of thousands of years before conditions became suitable for matter to begin clustering together under the influence of gravity. The seeds of all cosmic structure, including the massive galaxy clusters we observe today, were planted in the first fraction of a second after the Big Bang during a period called cosmic inflation. During this brief but dramatic epoch, quantum fluctuations in the fabric of space-time itself were stretched to macroscopic scales by the exponential expansion of space. These tiny variations in density, initially smaller than subatomic particles, would eventually grow to become the largest structures in the universe. After inflation ended and the universe settled into a more leisurely expansion, these density fluctuations remained imprinted in the distribution of matter and energy. For the first 380,000 years, the universe was opaque to light, filled with a hot plasma of protons, electrons and photons in constant interaction. Matter couldn't collapse under its own gravity during this era because radiation pressure from the photons kept pushing particles apart. The universe needed to cool below 3,000 degrees Kelvin before electrons and protons could combine into neutral hydrogen atoms, an event astronomers call recombination. Once recombination occurred and the universe became transparent, gravity finally had its chance to begin building structures. The slight overdensities left over from inflation began to attract surrounding matter, growing denser and more massive over time. Dark matter, which doesn't interact with radiation the way ordinary matter does, had actually begun clustering slightly earlier, creating gravitational wells that ordinary matter would fall into once recombination was complete. These early dark matter structures, called dark matter halos, served as the gravitational scaffolding for all subsequent structure formation. The smallest halos, containing perhaps 1,000,000 times the mass of our Sun in dark matter, were the first to collapse and virialize, reaching a stable configuration where the kinetic energy of particles balanced against gravitational collapse. Within these small halos, the ordinary matter that had fallen in could cool and condense enough for the first stars to ignite, probably when the universe was only 100 million years old. The formation of the first stars marked a crucial turning point in cosmic history. These massive, short-lived stars, made almost entirely of hydrogen and helium from the Big Bang, blazed with incredible intensity, producing the first heavy elements through nuclear fusion in their cores. When these stars exploded as supernovae after just a few million years, they enriched the surrounding gas with these newly forged elements, forever changing the chemistry of the universe. As time progressed, dark matter halos continued to grow through accretion and mergers. Smaller halos fell into larger ones, building up increasingly massive structures. By the time the universe was a few 100 million years old, halos massive enough to host entire galaxies had formed. These early galaxies were quite different from the majestic spirals and ellipticals we see today, likely appearing as irregular clumps of young stars embedded in vast clouds of gas. The first galaxy clusters began to assemble when the universe was between 1 and 2 billion years old, as multiple galaxy-hosting halos fell together into even larger dark matter halos. These protoclusters, as astronomers call them, were loose associations of galaxies still in the process of falling toward their common center of gravity. The galaxies within them were actively forming stars at prodigious rates, fed by the vast reservoirs of gas flowing into the growing cluster along cosmic filaments. The process of cluster formation was far from gentle. As galaxies fell into the growing cluster potential, they accelerated to tremendous velocities, sometimes exceeding 1,000 kilometers per second. When galaxies passed close to one another at these speeds, gravitational tidal forces could strip away their outer regions, sending streams of stars into intergalactic space. Direct collisions between galaxies, while rare given the vast spaces between them, did occasionally occur, triggering intense bursts of star formation as gas clouds within the galaxies collided and compressed. Perhaps even more significant than galaxy interactions was the heating of gas as it fell into the cluster. As gas accelerated down into the deep gravitational well of the cluster, it heated through a process called virial shock heating, reaching temperatures of millions of degrees. This hot gas, known as the intracluster medium, would eventually contain more ordinary matter than all the galaxies in the cluster combined, glowing brightly in X-rays and playing a crucial role in the subsequent evolution of cluster galaxies. The formation of the intracluster medium marked the transition from a protocluster to a true galaxy cluster. Once this hot gas filled the space between galaxies, it began to influence their evolution in profound ways. Galaxies moving through this medium experienced ram pressure stripping, where the pressure of the hot gas stripped away their own gas reservoirs, eventually quenching their ability to form new stars. This process would transform many spiral galaxies into the red and dead elliptical galaxies that dominate cluster cores today. During these early epochs of cluster formation, the universe was a much more active place than it is today. The cosmic star formation rate peaked when the universe was about 3 billion years old, with galaxies producing stars at rates 10 times higher than typical galaxies today. Galaxy clusters forming during this period were sites of particularly intense activity, with numerous galaxies undergoing starbursts, active galactic nuclei blazing as supermassive black holes consumed in falling matter, and galaxy mergers occurring frequently. The hierarchical nature of structure formation meant that clusters continued to grow over time by accreting smaller groups and individual galaxies from their surroundings. This process was not uniform, but occurred preferentially along the filaments of the cosmic web, creating elongated structures that would eventually virialize into roughly spherical clusters. The largest clusters formed at the intersections of multiple filaments, where the supply of infalling matter was greatest. Observations of distant galaxy clusters provide us with direct glimpses of this formation process in action. When we observe a cluster billions of light years away, we're seeing it as it was billions of years ago during its assembly phase. These observations reveal clusters in various stages of formation, from loose groups of galaxies just beginning to fall together to more evolved systems with established hot gas halos and populations of elliptical galaxies in their cores. The role of supermassive black holes in cluster formation has become increasingly apparent through modern observations. Nearly every galaxy hosts a supermassive black hole at its centre, and these black holes were particularly active during the epoch of cluster assembly. As matter fell toward these black holes, it formed accretion disks that blazed with radiation, creating what astronomers call active galactic nuclei or quasars. The energy output from these active black holes could rival the combined light of all the stars in their host galaxies. This energy injection from supermassive black holes had important effects on cluster formation. The radiation and jets produced by active galactic nuclei could heat surrounding gas, preventing it from cooling and forming stars. This feedback mechanism helped regulate star formation in cluster galaxies and may have been responsible for establishing the observed relationship between black hole mass and galaxy properties that we see today. The chemical enrichment of galaxy clusters proceeded throughout their formation history. Each generation of stars produced heavier elements through nuclear fusion, and stellar winds and supernovae expelled these elements into the surrounding medium. In the dense environments of forming clusters, this enriched gas was retained by the cluster's gravity rather than escaping into intergalactic space. Over billions of years, this process built up substantial reservoirs of heavy elements in the intracluster medium, creating a fossil record of the cluster's star formation history. The merger history of galaxy clusters left distinctive signatures that astronomers can still observe today. When two clusters collided, the galaxy's hot gas and dark matter behaved differently during the merger. Galaxies, being essentially collisionless, pass through each other with only gravitational interactions. The hot gas in the two clusters, however, collided and shocked, heating to even higher temperatures and sometimes being displaced from the galaxies and dark matter. These merging clusters provide some of our best evidence for the existence of dark matter, as we can see the separation between the visible matter and the gravitational mass. By the time the universe was about 5 billion years old, many of the features we associate with modern galaxy clusters were in place. Massive elliptical galaxies dominated the cluster cores, surrounded by hot X-ray emitting gas and embedded in vast dark matter halos. The clusters had largely settled into virial equilibrium, with the motions of galaxies balanced against gravitational collapse. However, clusters continued to evolve through ongoing accretion and occasional major mergers, processes that continue to the present day. The architecture of galaxy clusters. When we examine a galaxy cluster in detail, we discover an architecture of stunning complexity and scale, with structures ranging from individual stars to vast dark matter halos spanning millions of light years. Each cluster is a self-contained universe of sorts, with its own population of galaxies, its own atmosphere of superheated gas, and its own gravitational domain that influences everything within and around it. At the heart of most massive galaxy clusters lies a single dominant galaxy, often called the brightest cluster galaxy, or BCG. These galaxies are among the most massive and luminous galaxies in the universe, sometimes containing over 1 trillion stars and extending for hundreds of thousands of light years. Unlike the spiral galaxies that grace many astronomical images, brightest cluster galaxies are typically giant ellipticals, showing little structure beyond a smooth distribution of old red stars that grows gradually fainter with distance from the centre. The formation of these central giants is intimately connected to the cluster's evolution. As galaxies fall toward the cluster centre over billions of years, some inevitably merge with the central galaxy, adding their stars to its vast collection. This process, called galactic cannibalism, has built up the brightest cluster galaxies through countless mergers, creating galaxies so massive that they can actually influence the evolution of the entire cluster through their gravity and the activity of their central supermassive black holes. Surrounding the brightest cluster galaxy, the cluster core contains a high concentration of other elliptical and lenticular galaxies. This region, typically extending for about 500,000 light-years from the cluster center, represents the oldest and most evolved part of the cluster. The galaxies here have had billions of years to interact with each other and with the cluster environment, stripping away their gas and transforming their stellar populations. The stellar density in cluster cores can be remarkable, with dozens of major galaxies packed into a volume that might contain only one or two galaxies in less dense regions of the universe. Moving outward from the core, we encounter a transition region where the galaxy population begins to change. Here we find a mixture of galaxy types, including some spiral galaxies that have managed to retain their distinctive arms despite the harsh cluster environment. Many of these spirals show signs of environmental stress, such as truncated disks where ram pressure stripping has removed their outer gas, or disturbed morphologies from gravitational interactions with other cluster members. The galaxy population in clusters follows distinctive patterns that astronomers have studied for decades. One of the most striking is the morphology-density relation, which describes how the types of galaxies change with local density. In the dense cluster cores, elliptical and lenticular galaxies dominate, making up sometimes 90% or more of the galaxy population. In the less dense outer regions, spiral galaxies become more common, though they never dominate the way they do in low-density environments like our local group. Another fundamental characteristic of cluster galaxies is their color distribution. When astronomers plot the colors and brightnesses of cluster galaxies, they find that most fall along a tight relation called the red sequence. These are galaxies that have ceased forming new stars, leaving only older, redder stellar populations. The existence of this red sequence tells us that something about the cluster environment efficiently shuts down star formation in galaxies, transforming blue, star-forming galaxies into red, quiescent ones. The velocities of galaxies within clusters reveal the immense gravitational forces at work. Galaxies orbit through the cluster at speeds that typically range from 500 to 1500 kilometers per second, fast enough to traverse the entire cluster in about 1 billion years. These high velocities were actually one of the first pieces of evidence for dark matter, as the galaxies move far too fast to be held by the gravity of the visible matter alone. The distribution of these galaxy velocities follows predictable patterns that tell us about the cluster's dynamical state. In a relaxed, virialized cluster, the velocities follow a Gaussian distribution centered on the cluster's average velocity. However, in clusters that have recently undergone mergers or are still assembling, we often see multiple velocity peaks or asymmetric distributions that reveal the ongoing dynamical evolution. Between the galaxies lies the intracluster medium, a vast atmosphere of hot gas that represents one of the cluster's most important components. This gas, heated to temperatures between 10 million and 100 million degrees Kelvin, emits powerful X-ray radiation that allows us to map its distribution and properties. The gas density is highest in the cluster core and decreases gradually with radius, following the gravitational potential of the cluster's dark matter halo. The total mass of gas in the intracluster medium typically exceeds the combined mass of all the stars in the cluster's galaxies by a factor of 2 to 5. This gas is not primordial but has been enriched with heavy elements produced by generations of stars in the cluster galaxies. The distribution of these elements provides clues about how and when the gas was expelled from galaxies and mixed into the intracluster medium. The temperature structure of the intracluster medium reveals the cluster's formation history. In relaxed clusters, the gas temperature generally increases with radius until reaching a peak at about 1/3 of the virial radius, then declining in the outer regions. This temperature profile reflects the way gas heats as it falls into the cluster's gravitational potential. In merging clusters, we often see temperature substructures and shock fronts where gas from different subclusters collides and heats. Some clusters show evidence of cooling flows in their cores, where the dense gas radiates away its thermal energy and should cool catastrophically. However, observations show that very little gas actually cools all the way down to form stars, suggesting that some heating mechanism, likely feedback from the central galaxy's supermassive black hole, maintains the gas at high temperatures. This balance between cooling and heating is crucial for understanding how clusters evolve. The intracluster medium also contains magnetic fields that thread through the gas and influence its behavior. These fields, while weak compared to those in galaxies, can affect the propagation of cosmic rays, the dynamics of the gas, and the acceleration of particles in cluster shocks. Radio observations reveal that some clusters host vast radio halos and relics, structures that extend for millions of light years and shine through synchrotron emission from relativistic electrons spiraling in the magnetic fields. Surrounding all the visible components of a galaxy cluster is its dark matter halo, the invisible scaffolding that holds everything together. Dark matter comprises approximately 85% of a cluster's total mass, creating a gravitational potential well that extends far beyond the visible galaxies. The distribution of dark matter can be mapped through gravitational lensing, where the cluster's gravity bends light from background galaxies, creating distorted and sometimes multiple images. The dark matter distribution in clusters typically follows what astronomers call a Navarro-Frenk-White profile, with density decreasing gradually from the center outward. However, the detailed distribution can be quite complex, with substructures corresponding to infalling galaxy groups and remnants of past mergers. These dark matter subhalos host individual galaxies or groups of galaxies, maintaining their identity even as they orbit within the larger cluster potential. The outer regions of galaxy clusters, called the infall regions, represent the frontier where new galaxies are being incorporated into the cluster. Here, galaxies and groups falling in for the first time experience their initial interactions with the cluster environment. This is where spiral galaxies begin their transformation into the red, dead galaxies of the cluster core, a process that can take billions of years to complete. The three-dimensional structure of galaxy clusters is complex and often asymmetric. While we might imagine clusters as spherical, they're actually typically elongated along the directions of major filaments feeding the matter. This triaxial structure affects everything from galaxy orbits to the distribution of hot gas and the propagation of merger shocks. Understanding this three-dimensional structure requires sophisticated observations and modelling. Substructure within galaxy clusters provides evidence for ongoing assembly and past merger events. Many clusters contain distinct subclusters, groups of galaxies that are falling into the main cluster but haven't yet fully merged. These substructures can be identified through their concentrations of galaxies, peaks in the X-ray emission from hot gas, or clumps in the weak lensing mass maps. The amount and distribution of substructure tells us about the cluster's recent accretion history. The edges of galaxy clusters are not sharp boundaries but gradual transitions into the surrounding cosmic web. The virial radius, typically about 3 to 5 million light-years from the cluster center, marks the approximate edge of the virialized region where galaxies are in orbital equilibrium. Beyond this lies the infall region, extending perhaps twice as far, where galaxies and gas are still falling toward the cluster for the first time. At the largest scales, galaxy clusters are connected to the cosmic web through filaments of galaxies and gas. These filaments funnel matter into the cluster, providing the raw material for continued growth. Recent observations have begun to detect the warm, hot intergalactic medium in these filaments, gas at temperatures of hundreds of thousands to millions of degrees that represents a significant fraction of the ordinary matter in the universe. Dark matter, the invisible sculptor. The story of dark matter in galaxy clusters begins with a puzzle that emerged in the 1930s when Swiss astronomer Fritz Zwicky studied the Coma cluster, one of the nearest massive galaxy clusters to Earth. By measuring the velocities of galaxies within the cluster and applying the virial theorem, which relates the kinetic energy of a system to its gravitational potential energy, Zwicky calculated that the cluster must contain far more mass than could be accounted for by the visible galaxies alone. He coined the term dunkle materie, or dark matter, to describe this missing mass, though his discovery would not be fully appreciated for decades. The evidence for dark matter in galaxy clusters has only grown stronger with time and improved observations. When we measure the velocities of hundreds or thousands of galaxies in a cluster, we find they're moving at speeds that would allow them to escape the cluster's gravity entirely if only the visible matter were present. To hold these fast-moving galaxies in gravitational bondage requires approximately 5 to 10 times more mass than we can see in the form of stars and gas. This invisible mass, whatever its nature, dominates the gravitational landscape of galaxy clusters. Dark matter in clusters doesn't emit, absorb, or reflect light, making it invisible to our telescopes across the entire electromagnetic spectrum. We can only detect its presence through its gravitational effects on visible matter and light. This gravitational influence is profound, shaping everything from the orbits of individual galaxies to the large-scale distribution of matter in the universe. Without dark matter, galaxy clusters, as we know them, simply could not exist. The distribution of dark matter within galaxy clusters follows patterns that theorists have worked to understand through complex computer simulations. These simulations, which model the gravitational interactions of billions of dark matter particles over cosmic time, predict that dark matter should form halos with specific density profiles. The centers of these halos should be dense, with the density falling off gradually with distance from the center. Remarkably, observations of real clusters through gravitational lensing confirm these predictions, showing that dark matter is distributed in just the way the simulations suggest. Gravitational lensing has become our most powerful tool for mapping dark matter in galaxy clusters. When light from distant galaxies passes through or near a cluster, the cluster's gravity, dominated by dark matter, bends the light paths, causing the background galaxies to appear distorted or even multiply imaged. By carefully measuring these distortions, astronomers can reconstruct the distribution of mass in the cluster, creating detailed maps of where the dark matter resides. These maps reveal that dark matter forms a smooth extended halo that encompasses all the visible components of the cluster. One of the most dramatic demonstrations of dark matter's reality comes from observations of colliding galaxy clusters. The Bullet cluster, a system where two clusters have passed through each other, provides what many consider the smoking gun evidence for dark matter. In this collision, the hot gas from the two clusters, visible in X-rays, collided and slowed down, becoming separated from the galaxies which passed through largely unaffected. Gravitational lensing reveals that most of the mass, the dark matter, stayed with the galaxies rather than the gas, exactly as predicted if dark matter exists and interacts only gravitationally. Similar cluster collisions have been observed in other systems, each confirming the same pattern. The dark matter halos pass through each other essentially unaffected, while the ordinary matter in the form of hot gas experiences ram pressure and shocks that slow it down and heat it up. These observations place strong constraints on the properties of dark matter, showing that it must have very small interaction cross-sections with both itself and ordinary matter beyond gravity. The nature of dark matter particles remains one of the greatest mysteries in physics. Leading theories suggest dark matter consists of weakly interacting massive particles, or WIMPs, hypothetical particles, that would have been produced in the early universe and survived to the present day. These particles would need to be stable over cosmic time, interact primarily through gravity, and have masses perhaps hundreds of times that of a proton. Despite decades of searches in underground laboratories and particle accelerators, no direct detection of dark matter particles has been confirmed. Alternative theories for dark matter include axions, extremely light particles that could solve certain problems in particle physics, and primordial black holes formed in the early universe before the first stars. Some scientists have even proposed modifications to our theory of gravity that could explain the observations without invoking dark matter, though these theories struggle to explain the full range of evidence, particularly from cluster collisions. Within galaxy clusters, dark matter creates a complex landscape of gravitational potentials. The main cluster halo is not smooth, but contains thousands of smaller subhalos, each hosting a galaxy or group of galaxies. These subhalos orbit within the main halo, occasionally merging with each other or being disrupted by tidal forces. The survival and evolution of these subhalos depends on their dark matter content, with more massive subhalos better able to resist the tidal forces of the main cluster. The relationship between galaxies and their dark matter halos is fundamental to understanding galaxy evolution in clusters. Each galaxy sits at the center of its own dark matter subhalo, which protects it from complete disruption as it orbits through the cluster. However, the outer regions of these subhalos can be stripped away by tidal forces, a process called tidal stripping, which gradually reduces the galaxy's dark matter content and can affect its ability to retain gas and continue forming stars. Dark matter also influences the heating and distribution of the intracluster medium. The deep gravitational potential, well created by the dark matter halo, determines how hot the gas becomes as it falls into the cluster. The temperature of the intracluster medium, typically tens of millions of degrees, directly reflect the depth of the dark matter potential. More massive clusters with more dark matter have hotter gas, creating a tight correlation between X-ray temperature and total cluster mass. The dark matter distribution affects how sound waves and shocks propagate through the intracluster medium. When clusters merge, the collision generates enormous shocks that heat the gas and accelerate particles to relativistic speeds. The geometry and strength of these shocks depend on the distribution and relative velocities of the dark matter halos, making shock structures another probe of the invisible dark matter. Computer simulations of structure formation in a universe dominated by cold dark matter have been remarkably successful in reproducing the observed properties of galaxy clusters. These simulations start with tiny density fluctuations in the early universe and follow how gravity causes these fluctuations to grow over billions of years. Dark matter, being the dominant form of matter, drives this growth, with ordinary matter falling into the potential wells created by dark matter and eventually forming stars and galaxies. The simulations predict a hierarchy of structure, with small dark matter halos forming first and subsequently merging to build larger and larger structures. This hierarchical assembly naturally produces the range of cluster masses we observe, from small groups with just a few galaxies to massive clusters containing thousands. The simulations also predict the existence of vast numbers of small dark matter halos that contain no galaxies at all, too small to have formed stars, but still orbiting within galaxy clusters. One intriguing prediction of dark matter simulations is the existence of dark matter streams and caustics in galaxy clusters. As dark matter falls into a cluster, it doesn't immediately mix smoothly, but can maintain coherent streams for billions of years. These streams create caustics, regions where the dark matter density is temporarily enhanced, which should produce distinctive signatures in gravitational lensing observations. Detecting these features would provide another test of our understanding of dark matter. The dark matter in galaxy clusters may also play a role in the production of high-energy particles and radiation. Some theories predict that dark matter particles could annihilate or decay, producing gamma rays or other particles that we could detect. Galaxy clusters, with their enormous dark matter content, would be ideal places to search for such signals. While no confirmed detections have been made, the non-detection places constraints on the properties of dark matter particles. Dark matter's gravitational influence extends far beyond the visible boundaries of galaxy clusters. The dark matter halo of a massive cluster can extend for 10 million light-years or more, reaching out into the surrounding cosmic web. This extended halo affects the motion of galaxies and gas far from the cluster center, creating an infall region where matter is being drawn toward the cluster but hasn't yet reached orbital equilibrium. The way dark matter clusters and forms structures provides crucial information about its properties. The fact that we see structure on all scales, from dwarf galaxies to galaxy clusters, tells us that dark matter must be cold, meaning the particles were moving slowly when structures began to form. Hot dark matter, particles moving at relativistic speeds, would have erased small-scale structures, producing a universe very different from what we observe. Recent observations have begun to probe the dark matter distribution in clusters with unprecedented precision. Combining gravitational lensing with other observations like X-ray emission and galaxy velocities allows astronomers to break degeneracies and better constrain the dark matter distribution. These multi-wavelength approaches are revealing subtle features in dark matter halos that challenge and refine our theoretical understanding. The hot gas between galaxies. Between the galaxies that populate galaxy clusters lies an ocean of superheated gas, invisible to our eyes but blazing brilliantly in X-rays. This intracluster medium represents one of the most extreme environments in the universe, with temperatures reaching 100 million degrees Kelvin, hot enough that atoms are completely ionized and electrons move at substantial fractions of the speed of light. This gas, though incredibly tenuous by earthly standards, with densities billions of times lower than the air we breathe, contains more ordinary matter than all the stars in all the galaxies within the cluster combined. The discovery of this hot gas revolutionized our understanding of galaxy clusters in the 1970s, when X-ray satellites first detected the brilliant emission from cluster cores. Before these observations, astronomers thought clusters were simply collections of galaxies moving through empty space. The revelation that clusters are filled with vast atmospheres of superheated plasma transformed our picture of these cosmic structures and provided new tools for studying their properties and evolution. The origin of the intracluster medium traces back to the formation of the cluster itself. As matter fell into the growing gravitational potential well of the cluster, over billions of years, it accelerated to tremendous velocities. When this infalling gas encountered the forming cluster, it experienced violent shock heating, converting its kinetic energy into thermal energy. These accretion shocks, occurring at the outskirts of clusters even today, heat incoming gas from temperatures of perhaps 10,000 degrees to tens of millions of degrees in an instant. Not all the gas in the intracluster medium arrived directly from the cosmic web. A significant fraction was expelled from the cluster galaxies themselves through various processes over cosmic time. Supernovae explosions, powerful winds from massive stars, and energy injection from supermassive black holes all contributed to stripping gas from galaxies and adding it to the intracluster medium. This expelled gas carried with it the heavy elements forged in stellar furnaces, enriching the intracluster medium with metals that serve as traces of the cluster's star formation history. The temperature of the intracluster medium provides a direct measure of the cluster's gravitational potential. The gas is held in hydrostatic equilibrium, with thermal pressure balancing against gravitational collapse. More massive clusters have deeper gravitational wells, requiring higher gas temperatures to maintain this balance. This relationship between temperature and mass makes X-ray observations powerful tools for measuring cluster masses and understanding their place in the cosmic hierarchy. The distribution of gas within clusters follows characteristic patterns that reveal the cluster's dynamical state. In relaxed, undisturbed clusters, the gas density peaks smoothly at the center and declines gradually with radius. The temperature structure is more complex, often showing a slight decrease in the very center, where the dense gas can radiate energy more efficiently, surrounded by a region of roughly constant temperature, then declining in the outer regions, where the gravitational potential becomes shallower. This seemingly simple picture becomes far more complex in clusters that have experienced recent mergers or are still assembling. When two clusters collide, their gas components, unlike the collisionless galaxies and dark matter, cannot pass through each other freely. Instead, the gas clouds collide at velocities of thousands of kilometers per second, generating enormous shock waves that propagate through the intracluster medium. These shocks, among the largest and most energetic phenomena in the universe since the Big Bang, heat the gas to even higher temperatures and can accelerate particles to cosmic ray energies. The shock structures in merging clusters create spectacular features visible in X-ray observations. Cold fronts, sharp discontinuities in gas temperature and density mark the boundaries between gas from different subclusters. These fronts can remain surprisingly sharp for billions of years, indicating that transport processes like thermal conduction must be suppressed, likely by magnetic fields threading through the plasma. Shock fronts appear as edges where the gas temperature jumps dramatically, marking the locations where kinetic energy is being converted to heat. One of the most fascinating aspects of the intracluster medium is the cooling flow problem that has puzzled astronomers for decades. In the dense cores of many clusters, the gas radiates energy so efficiently that it should cool dramatically, with cooling times shorter than the age of the cluster. Simple calculations suggest that hundreds or even thousands of solar masses of gas per year should cool from X-ray emitting temperatures down to temperatures where stars could form. Yet observations show that very little cold gas or star formation actually occurs in cluster cores, far less than predicted by simple cooling flow models. The solution to this cooling flow problem appears to involve feedback from the supermassive black holes lurking in the central galaxies of clusters. These black holes, though tiny compared to the cluster itself, can have profound effects on the surrounding medium. As matter falls toward the black hole, it forms an accretion disk that can launch powerful jets of relativistic particles. These jets inflate enormous bubbles in the intracluster medium, cavities filled with relativistic particles and magnetic fields that appear as dark regions in X-ray images. These bubbles, sometimes extending for hundreds of thousands of light-years, rise buoyantly through the cluster atmosphere like hot air balloons through Earth's atmosphere. As they rise, they do mechanical work on the surrounding gas, lifting cooler gas from the center and inducing turbulent motions that help distribute heat throughout the core region. The energy input from this active galactic nucleus feedback appears to be remarkably well tuned to balance radiative cooling, maintaining a state of quasi-equilibrium that prevents catastrophic cooling while allowing some gas to cool and fuel the black hole. The chemical composition of the intracluster medium provides a fossil record of the cluster's star formation history. Heavy elements like iron, silicon, and oxygen, produced in supernova and stellar winds, are present at about 1/3 to 1/2 the concentration found in the Sun. This substantial metal content indicates that clusters have retained most of the metals produced by their galaxies over cosmic time, making them excellent laboratories for studying chemical evolution. The distribution of these elements is not uniform, but shows gradients and variations that reflect the history of gas stripping from galaxies and mixing in the intracluster medium. Different elements trace different stellar processes and populations. Iron comes primarily from type Ia supernova, the thermonuclear explosions of white dwarfs, while oxygen and other alpha elements come mainly from core collapse supernova of massive stars. The ratio of these elements in the intracluster medium tells us about the relative contributions of different types of stars to the cluster's chemical enrichment. Observations show that the iron abundance typically peaks in cluster cores, where the central galaxy has had billions of years to enrich its surroundings, while being more uniform at larger radii. The intracluster medium is magnetized, threaded by weak but important magnetic fields that influence many of its properties. These fields, typically a millionth the strength of Earth's magnetic field, affect heat conduction, particle acceleration, and the dynamics of the plasma. The origin of these magnetic fields remains uncertain, but they were likely amplified from tiny seed fields through turbulent dynamo processes during cluster formation and mergers. The magnetic fields create a kind of cosmic fabric that can suppress transport processes perpendicular to the field lines while allowing motion along them. Radio observations reveal that some clusters host diffuse radio emission on enormous scales, structures that would be invisible without the magnetic fields permeating the intracluster medium. Radio halos are roughly spherical regions of radio emission centered on clusters, extending for millions of light years and powered by relativistic electrons spiraling in the magnetic fields. Radio relics are elongated structures typically found in cluster outskirts, thought to trace shock fronts, where particles are accelerated to relativistic energies. These radio structures provide unique insights into the non-thermal components of the intracluster medium and the particle acceleration processes occurring in clusters. The turbulent motions within the intracluster medium, driven by ongoing accretion, galaxy motions, and active galactic nucleus feedback, play crucial roles in the cluster's evolution. This turbulence, with velocities of hundreds of kilometers per second, helps mix metals throughout the cluster, transport heat from hot to cool regions, and may provide pressure support that affects mass measurements. Recent observations have begun to measure these turbulent velocities directly through Doppler broadening of X-ray emission lines, opening new windows into the dynamics of the intracluster medium. Sound waves propagate through the intracluster medium, carrying energy and information across the cluster. These sound waves, with periods of tens of millions of years and wavelengths of hundreds of thousands of light years, are generated by active galactic nucleus outbursts and merger events. In the Perseus cluster, astronomers have detected ripples in the X-ray emission that represent sound waves propagating outward from the central black hole, waves that would correspond to musical notes 57 octaves below middle C if we could hear them. The pressure of the intracluster medium has profound effects on the galaxies moving through it. Ram pressure stripping occurs when a galaxy's motion through the medium creates a wind that can strip away its own gas, much like wind removing leaves from a tree. This process is particularly effective for galaxies falling into clusters at high velocities and can completely strip a galaxy of its gas in less than 1 billion years. The stripped gas forms spectacular tails behind the galaxies, sometimes extending for hundreds of thousands of light years, creating structures astronomers call jellyfish galaxies for their resemblance to the marine creatures. The outer boundaries of the intracluster medium are not sharp edges, but gradual transitions into the lower density gas of the cosmic web. At the virial radius, typically 3 to 5 million light years from the cluster center, the gas density has dropped to just a few times the cosmic mean density. Beyond this, in the infall regions, gas is still falling toward the cluster but hasn't yet been shock heated to X-ray emitting temperatures. This warm-hot intergalactic medium, at temperatures of hundreds of thousands to a few million degrees, represents a significant reservoir of baryons that clusters continue to accrete. The intracluster medium serves as a cosmic laboratory for studying fundamental physics under extreme conditions impossible to reproduce on Earth. The low densities mean that particles can travel vast distances without colliding, creating a nearly collisionless plasma where collective electromagnetic effects dominate over particle collisions. The combination of high temperatures, low densities and weak magnetic fields creates conditions where exotic plasma physics processes can occur, teaching us about the behavior of matter in extreme environments throughout the universe. Observations of the intracluster medium across different wavelengths reveal its multifaceted nature. X-ray observations show the thermal emission from the hot gas, revealing its temperature, density, and metal abundance. Radio observations detect synchrotron emission from relativistic particles and can trace magnetic field structures. Optical observations can detect emission lines from gas at intermediate temperatures, particularly in filaments and cooling regions. The Sunyaev-Zeldovich effect, where cosmic microwave background photons are scattered to higher energies by hot electrons, provides another probe of the gas pressure independent of distance, making it valuable for studying distant clusters. The evolution of the intracluster medium over cosmic time reflects the growth and evolution of clusters themselves. In the early universe, when clusters were first assembling, the intracluster medium was likely more turbulent and inhomogeneous, with active accretion and frequent mergers driving strong shocks and mixing. As clusters aged and relaxed, their intracluster medium settled into more regular configurations, though ongoing accretion and feedback ensure that true equilibrium is never achieved. The metal content of the intracluster medium has increased over time as successive generations of stars in cluster galaxies enrich their surroundings. Future observations with next-generation X-ray telescopes promise to revolutionize our understanding of the intracluster medium. High-resolution spectroscopy will map gas velocities and turbulence in unprecedented detail, while improved sensitivity will detect the faint emission from cluster outskirts where gas is still falling in. These observations will address fundamental questions about how clusters grow, how energy is transported through the plasma, and how the intracluster medium influences galaxy evolution. Notable galaxy clusters throughout the universe. Across the vast expanse of the observable universe, certain galaxy clusters stand out as particularly remarkable examples of these cosmic giants, each offering unique insights into the nature and evolution of the largest gravitationally bound structures in existence. These clusters serve as laboratories for understanding everything from dark matter to galaxy evolution, and their study has revolutionized our understanding of cosmology and astrophysics. The Virgo cluster holds special significance as our nearest large cluster neighbour, lying approximately 54 million light-years away in the constellation Virgo. This massive accumulation of galaxies serves as the gravitational heart of our local supercluster, influencing the motion of thousands of galaxies, including our own Milky Way, across a region spanning more than 100 million light-years. The Virgo cluster contains somewhere between 1,300 and 2,000 galaxies, though the exact number depends on where one draws the boundary between the cluster and its surroundings. At the centre of the Virgo cluster sits Messier 87, one of the most massive galaxies known, containing several trillion stars and hosting a supermassive black hole of 6.5 billion solar masses. This black hole gained worldwide fame in 2019 when the Event Horizon Telescope collaboration produced the first direct image of a black hole's event horizon, showing the glowing ring of hot gas circling the gravitational abyss. Messier 87 also produces a spectacular jet of relativistic particles extending thousands of light-years from its core, powered by the spinning black hole and its surrounding accretion disk. The Virgo cluster's relative proximity makes it an ideal laboratory for studying cluster processes in exquisite detail. Astronomers have mapped the orbits of individual galaxies, traced streams of stars torn from disrupted galaxies, and observed gas being stripped from infalling spirals in real time. The cluster shows clear evidence of substructure, with several distinct subclusters in various stages of merging with the main body, providing insights into how clusters grow through hierarchical assembly. Moving farther into the cosmos, we encounter the Coma cluster, located approximately 320 million light-years away in the constellation Coma Berenices. This cluster holds historical importance as the site where Fritz Zwicky first discovered evidence for dark matter in the 1930s. The Coma cluster is remarkably rich, containing over 1,000 galaxies brighter than magnitude 19.5 within its central region, making it one of the densest concentrations of galaxies in the nearby universe. The Coma cluster represents a textbook example of a relaxed evolved cluster that has had billions of years to settle into dynamical equilibrium. Its galaxy population is dominated by elliptical and lenticular galaxies, with very few spirals remaining, indicating that environmental processes have been highly effective at transforming galaxies. The cluster's hot gas distribution is smooth and regular, centered on two giant elliptical galaxies that likely merged from separate cluster cores billions of years ago. X-ray observations reveal a temperature of about 100 million degrees Kelvin in the cluster core, among the hottest intra-cluster medium temperatures observed. The Perseus cluster, approximately 240 million light-years distant, has become famous for its active galactic nucleus feedback and the remarkable structures this creates in its intracluster medium. The central galaxy, NGC 1275 or Perseus A, hosts an active supermassive black hole that has been inflating bubbles in the surrounding hot gas for hundreds of millions of years. These bubbles, visible as cavities in X-ray images, have risen through the cluster atmosphere, creating a complex structure of ripples, sound waves, and weak shocks that regulate cooling in the cluster core. The Perseus cluster has provided astronomers with the most detailed view of how supermassive black holes can influence entire galaxy clusters. The sound waves propagating through its intra-cluster medium have been mapped in exquisite detail, revealing how mechanical energy from the black hole is distributed throughout the core. The cluster also shows beautiful filaments of cooler gas drawn out into long threads by magnetic fields and buoyant bubbles, creating some of the most visually striking structures observed in any cluster. The Fornax cluster, though smaller than giants like Coma or Perseus, offers unique insights as the second nearest cluster after Virgo at about 62 million light-years away. This cluster is particularly interesting because it appears to be in a younger evolutionary state than many rich clusters, still actively accreting galaxies from its surroundings. The cluster contains about 60 major galaxies concentrated in a relatively small volume, making it an excellent target for studying galaxy interactions and environmental effects in a less extreme environment than massive clusters. One of the most spectacular cluster discoveries of recent decades is the Bullet cluster, officially designated 1E Rho 657558, located approximately 3.7 billion light-years away. This system consists of two clusters that have collided and passed through each other, creating what many consider the most direct evidence for the existence of dark matter. The collision, which occurred approximately 150 million years ago from our perspective, separated the different components of the clusters in a remarkable way. In the Bullet cluster collision, the hot gas from the two clusters, visible in X-ray observations, collided and was slowed by ram pressure, becoming displaced from the galaxies which passed through largely unaffected. Gravitational lensing observations reveal that the bulk of the mass, the dark matter, remained with the galaxies rather than the gas. This separation of the different mass components cannot be explained by modified gravity theories and provides compelling evidence that dark matter is real and interacts primarily through gravity alone. The Abell 2744 cluster, known as Pandora's cluster, represents one of the most complex merging systems ever observed. Located about 3.5 billion light-years away, this cluster appears to be the result of a simultaneous collision of at least 4 separate clusters, creating a cosmic train wreck of unprecedented complexity. The system shows multiple shock fronts, displaced gas clouds, and a distribution of galaxies and dark matter that reveals the violent history of this cosmic pile-up. Pandora's cluster has become one of the most studied clusters in astronomy, targeted by the Hubble Space Telescope as part of the Frontier Fields program. These deep observations use the cluster's gravity as a natural telescope, magnifying distant galaxies behind it and allowing astronomers to study some of the earliest galaxies in the universe. The complex mass distribution of the merging system creates multiple critical curves for gravitational lensing, producing a rich field of magnified background galaxies at various distances. The Phoenix cluster, discovered in 2010 at a distance of about 5.7 billion light-years, shattered records as one of the most massive and luminous clusters known. What makes Phoenix truly exceptional is the prodigious rate of star formation in its central galaxy, forming stars at a rate of about 740 solar masses per year, the highest rate ever observed in a cluster center. This extreme star formation appears to be fueled by cooling gas from the intracluster medium, making Phoenix the strongest cooling flow cluster known. The Phoenix cluster challenges our understanding of feedback in cluster cores. Despite hosting an active supermassive black hole, the feedback appears insufficient to prevent cooling and star formation at the observed rates. This system may represent a brief phase in cluster evolution when cooling temporarily overwhelms heating, or it might indicate that our models of active galactic nucleus feedback need revision. The cluster also holds records for its X-ray luminosity and the mass of its central black hole, estimated at 20 billion solar masses. The El Gordo cluster, officially ACT CL J01224915, earned its nickname, meaning the Fat One, in Spanish for being the most massive cluster known at its distance of about 7 billion light-years. This cluster is another merging system, caught in the act of collision at a time when the universe was only half its current age. El Gordo's mass, exceeding 3 quadrillion solar masses, challenges models of structure formation. As such, massive clusters should be extremely rare at this early epoch. Studies of El Gordo provide insights into cluster formation in the early universe. The high collision velocity inferred from the separated gas and galaxy components suggests that the universe's expansion rate and matter density at that epoch allowed for the formation of surprisingly massive structures. The cluster also shows a prominent radio relic, evidence of particle acceleration in the merger shocks, demonstrating that the same physical processes operating in nearby clusters were already at work billions of years ago. The Abell 370 cluster has become iconic for the dramatic gravitational lensing arcs it produces, including the famous Dragon arc, a background galaxy stretched and magnified into a thin arc extending for hundreds of thousands of light-years across our view. Located about 4 billion light-years away, this cluster demonstrates the power of gravitational lensing for studying both the mass distribution of clusters and the properties of distant background galaxies that would otherwise be too faint to observe. The detailed mass modelling of Abell 370 required to explain its complex lensing features has revealed that the cluster consists of 2 major components in the process of merging. The distribution of dark matter mapped through weak and strong lensing shows 2 distinct peaks corresponding to the 2 subclusters, while the gas shows a more complex distribution influenced by the ongoing collision. This system illustrates how gravitational lensing can reveal cluster dynamics and dark matter distribution in ways impossible through other observations. The Norma cluster, also known as Abell 3627, remained hidden from astronomers for decades because it lies behind the plane of our Milky Way galaxy, in the so-called zone of avoidance, where dust and stars in our galaxy obscure extragalactic objects. When finally detected through radio and infrared observations that can penetrate the galactic dust, the Norma cluster was revealed to be one of the most massive clusters in the nearby universe, comparable to the Coma cluster in richness. The discovery of the Norma cluster helped solve the mystery of the Great Attractor, a gravitational anomaly that influences the motion of galaxies throughout our region of the universe. The cluster's enormous mass, combined with other structures in the same direction, contributes significantly to the gravitational pull that draws our local group and thousands of other galaxies toward this region of space at velocities of hundreds of kilometers per second. The Antlia cluster, though modest in size compared to giants like Coma or Perseus, has revealed important insights about cluster formation and evolution. Located about 130 million light-years away, this cluster appears to be in an early stage of assembly, with distinct groups of galaxies still falling together. The cluster's proximity and youth make it an excellent laboratory for studying how smaller structures merge to form larger clusters, a process that has shaped all clusters throughout cosmic history. Max J07.5 represents one of the most disturbed clusters known, showing evidence for multiple merger events occurring simultaneously. Located about 5.4 billion light-years away, this cluster exhibits an extraordinarily complex structure with at least 4 distinct subclusters involved in high-speed collisions. Radio observations reveal the largest radio relic known, extending for millions of light-years and marking the locations of merger shocks accelerating particles to near light speed. The complexity of Max J0717 makes it a challenging but rewarding target for testing our understanding of cluster physics. The multiple mergers create a variety of shock strengths and geometries, allowing astronomers to study particle acceleration under different conditions. The disturbed gravitational potential creates strong and complex gravitational lensing effects, producing multiple images of background galaxies that help map the dark matter distribution during this cosmic collision. The Hercules cluster, Abel 2151, provides an example of a young, irregular cluster still in the process of formation. Unlike relaxed clusters with smooth, centrally concentrated distributions of galaxies, Hercules shows multiple clumps and subgroups with no dominant central galaxy. This cluster, about 500 million light-years distant, offers insights into what many clusters might have looked like billions of years ago when they were first assembling from smaller groups. The SPT-CL J2344-42243 cluster, discovered through its Sunyaev-Zeldovich effect signature by the South Pole Telescope, holds the record as the most massive cluster known at its redshift of 1.4, when the universe was only 4.5 billion years old. This cluster, with a mass exceeding 1 quadrillion solar masses, demonstrates that massive clusters had already formed relatively early in cosmic history, providing important constraints on cosmological models and the growth of structure. Galaxy cluster evolution and dynamics. The evolution of galaxy clusters spans billions of years, encompassing processes that transform loose associations of galaxies into the massive, organized structures we observe today. This evolution continues even now, as clusters accrete new galaxies from their surroundings, merge with other clusters, and internally reorganize through the complex interplay of gravity, gas dynamics, and feedback processes. Understanding this evolution requires us to consider phenomena occurring on scales from individual stars to the larger structures in the universe. The hierarchical model of structure formation provides the framework for understanding how clusters evolve. In this picture, small structures form first and subsequently merge to build progressively larger ones. Galaxy clusters represent nearly the endpoint of this hierarchy, the larger structures that have had time to collapse and virialize since the Big Bang. Yet they continue to grow, accreting matter from the surrounding cosmic web and occasionally merging with other clusters in events that release more energy than any other phenomena since the Big Bang itself. The growth of clusters through accretion is an ongoing process that we can observe directly. Galaxies and smaller groups fall into clusters along filaments of the cosmic web, following paths determined by the cluster's gravitational pull and the large-scale structure of the universe. As these galaxies fall in, they accelerate to velocities of thousands of kilometers per second, transforming their orbital energy into kinetic energy. This infall process is not uniform, but happens preferentially along certain directions, creating asymmetries in the cluster structure that can persist for billions of years. When galaxies first encounter the cluster environment, they begin a transformation that will fundamentally alter their properties. Spiral galaxies entering clusters are typically rich in cold gas and actively forming stars. Their beautiful spiral arms traced by regions of young blue stars. As they plunge into the cluster, they encounter the hot intra-cluster medium at high velocity, creating ram pressure that can strip away their gas reservoirs in a process that astronomers have dubbed cosmic suffocation. Without gas to form new stars, these galaxies gradually redden as their stellar populations age, eventually becoming the red, dead galaxies that dominate cluster cores. The transformation of cluster galaxies involves multiple environmental mechanisms working in concert. Ram pressure stripping removes gas through direct hydrodynamic interaction with the intracluster medium. Tidal interactions with the cluster potential and other galaxies can distort galactic structures and trigger starbursts that rapidly consume remaining gas. Harassment from repeated high-speed encounters with other galaxies gradually heats stellar orbits and transforms spiral galaxies into featureless ellipticals. The relative importance of these mechanisms depends on the galaxy's mass, its orbit through the cluster, and the cluster's properties. Galaxy mergers, while less common in clusters than in lower density environments due to the high relative velocities, still play important roles in cluster evolution. When mergers do occur, typically in the lower velocity environments of cluster outskirts or within infalling groups, they can create the massive elliptical galaxies that populate cluster cores. The brightest cluster galaxies at cluster centers have grown through numerous mergers over cosmic time, cannibalizing smaller galaxies that spiral in through dynamical friction. The concept of dynamical friction is crucial for understanding how massive galaxies sink toward cluster centers. As a massive galaxy moves through the cluster, it gravitationally attracts nearby galaxies and dark matter, creating a wake of increased density behind it. This wake exerts a gravitational pull that opposes the galaxy's motion, gradually robbing it of orbital energy and causing it to spiral toward the cluster center. This process is most effective for the most massive galaxies, explaining why brightest cluster galaxies are typically found at or near cluster centers. Cluster mergers represent the most energetic events in the universe since the Big Bang, releasing energies of up to 10 to the 64th ergs over timescales of billions of years. When two clusters collide, their different components behave in distinct ways that reveal the nature of matter and the physics of extreme environments. The galaxies, being essentially collisionless, pass through each other with their trajectories altered only by gravity. The hot gas in the two clusters cannot interpenetrate freely but collides and shocks, heating to even higher temperatures, and sometimes being displaced from the galaxies and dark matter. The dynamics of cluster mergers depend on numerous factors, including the mass ratio of the merging clusters, their relative velocity, and the impact parameter of the collision. Head-on collisions produce different effects than off-center encounters, and mergers between equal mass clusters evolve differently than those involving a large cluster and a smaller group. Major mergers can take several billion years to complete, with the clusters passing through each other, reaching maximum separation, then falling back together one or more times before finally settling into a single, larger cluster. During mergers, shockwaves propagate through the intracluster medium at velocities of thousands of kilometers per second. These shocks heat the gas, sometimes to temperatures exceeding 200 million degrees Kelvin, and can accelerate particles to relativistic energies. The accelerated particles produce synchrotron radiation, visible as radio relics, elongated structures at cluster peripheries that trace the locations of merger shocks. These cosmic particle accelerators help us understand how cosmic rays are produced throughout the universe. The turbulence generated by mergers has lasting effects on cluster properties. Merger-induced turbulence can persist for billions of years, providing pressure support that affects mass measurements and heat transport throughout the cluster. This turbulence also amplifies magnetic fields through dynamo action, potentially explaining the micro-Gauss strength fields observed in cluster cores. The mixing driven by turbulence distributes metals throughout the intracluster medium, erasing gradients that would otherwise trace the history of galactic winds and star formation. Feedback processes, particularly from active galactic nuclei, play crucial roles in cluster evolution by regulating cooling and star formation in cluster cores. Without heating from active galactic nuclei, the dense gas in cluster centers would cool catastrophically, potentially forming stars at rates of thousands of solar masses per year. Instead, we observe that most clusters maintain a delicate balance between cooling and heating, with active galactic nucleus feedback providing just enough energy to offset radiative losses. The feedback cycle in clusters operates over timescales of tens to hundreds of millions of years. As gas cools in the cluster core, some falls onto the central supermassive black hole, triggering active galactic nucleus activity. The black hole launches jets that inflate bubbles in the intracluster medium, lifting cool gas and depositing energy through various mechanisms, including shocks, sound waves, and turbulence. This heating reduces cooling, eventually starving the black hole and reducing its activity until cooling again dominates and the cycle repeats. The evolution of the intracluster medium over cosmic time reflects the integrated history of star formation and feedback in cluster galaxies. Early in cluster history, when galaxies were more gas-rich and actively forming stars, supernovae and stellar winds expelled metal-enriched gas into the intracluster medium at higher rates than today. The metallicity of the intracluster medium thus provides a fossil record of past star formation, with measurements showing that most enrichment occurred more than 8 billion years ago when cosmic star formation peaked. Cool core clusters, those with dense, rapidly cooling gas in their centers, evolve differently from non-cool core clusters. Cool cores appear to be long-lived features that survive minor mergers but are disrupted by major mergers. The presence or absence of a cool core thus provides information about a cluster's recent merger history. Observations suggest that about half of relaxed clusters have cool cores, while recently merged systems rarely show this feature, though cool cores can reform given sufficient time without major disturbances. The evolution of cluster galaxy populations follows predictable patterns that depend on both cosmic time and location within the cluster. The morphology-density relation, whereby elliptical galaxies dominate dense regions, while spirals prefer low-density environments, becomes established early in cluster history and strengthens over time. The fraction of blue star-forming galaxies in clusters decreases with cosmic time, a trend known as the Butcher-Ummler effect, as environmental processes progressively quench star formation in cluster galaxies. Pre-processing in groups plays an important role in galaxy evolution before galaxies even reach the main cluster. Many galaxies fall into clusters not as isolated systems, but as members of groups that merge with the cluster. Within these groups, galaxies experience environmental effects similar to, but less extreme, than those in clusters, beginning their transformation from star-forming to quiescent before entering the cluster proper. This pre-processing may account for much of the galaxy transformation we attribute to cluster environments. The fossil record preserved in cluster stellar populations reveals their assembly history. The ages, metallicities, and alpha element enhancements of stars in cluster galaxies indicate when and how quickly they formed. Massive elliptical galaxies in cluster cores typically have old stellar populations formed in rapid bursts more than 10 billion years ago, while galaxies in cluster outskirts show more extended star formation histories. This radial gradient in stellar populations reflects the inside-out growth of clusters through accretion. Numerical simulations have become indispensable tools for understanding cluster evolution, allowing us to follow the complex interplay of gravity, hydrodynamics, and feedback over cosmic time. These simulations, run on the world's most powerful supercomputers, model the behavior of billions of dark matter particles, millions of gas elements, and thousands of galaxies as they interact and evolve. Modern simulations can reproduce many observed properties of clusters, though challenges remain in accurately modeling feedback processes and the behavior of gas on small scales. The future evolution of galaxy clusters will be shaped by the accelerating expansion of the universe driven by dark energy. As the universe expands ever faster, clusters will become increasingly isolated, with the flow of matter along cosmic filaments eventually ceasing. Clusters will continue to relax and evolve internally, but their growth through accretion will slow and eventually stop. In the far future, clusters will become island universes, isolated and slowly evaporating as their galaxies are occasionally ejected through gravitational interactions. Studies of cluster evolution at different cosmic epochs reveal how these systems have changed over time. High redshift clusters, observed as they were billions of years ago, show higher rates of star formation, more disturbed morphologies indicating recent assembly, and galaxy populations that differ markedly from those in nearby clusters. The evolution from these early systems to present-day clusters provides crucial tests of our models for structure formation and galaxy evolution. Superclusters and the largest structures. Beyond individual galaxy clusters lies an even grander scale of cosmic organization, where clusters themselves are grouped into superclusters, vast assemblages that represent the largest coherent structures in the universe. These superclusters, spanning hundreds of millions of light years and containing thousands of galaxies arranged in clusters, groups, and filaments, define the architecture of the cosmos on its largest scales. Unlike clusters, which are gravitationally bound and have separated from the cosmic expansion, superclusters are still expanding with the universe, their gravity insufficient to halt their constituent clusters from moving apart. Our own cosmic neighborhood, the Virgo supercluster, also known as the local supercluster, extends for more than 110 million light-years and contains roughly 100 galaxy groups and clusters. At its heart lies the Virgo cluster, whose gravity influences the motion of all galaxies within the supercluster, including our own Milky Way. The local supercluster has a distinctly flattened pancake-like shape, with most of its galaxies concentrated in a relatively thin plane, a configuration that arose from the gravitational collapse of a primordial density enhancement in the early universe. The discovery and mapping of superclusters required decades of painstaking observations to measure the distances to thousands of galaxies. As astronomers built three-dimensional maps of the galaxy distribution, patterns emerged that revealed structures far larger than individual clusters. These maps showed that galaxies are not randomly distributed through space, but organized into a cosmic web of filaments, walls, and voids, with superclusters forming the densest regions where multiple filaments intersect. The Shapley supercluster, located about 650 million light-years away in the constellation Centaurus, stands as one of the most massive concentrations of galaxies in the nearby universe. This immense structure contains dozens of galaxy clusters, including some of the most massive clusters known, all arranged in a complex configuration extending over several 100 million light-years. The Shapley supercluster's enormous mass exerts a significant gravitational pull on surrounding regions, contributing to the large-scale flows of galaxies we observe in our cosmic neighborhood. The gravitational influence of the Shapley supercluster extends far beyond its visible boundaries, affecting the motion of galaxies throughout our region of the universe. Our own local group, along with the entire local supercluster, is being drawn toward the Shapley supercluster at several hundred kilometers per second, part of a vast cosmic flow that involves millions of galaxies streaming through space under the influence of these massive structures. This motion, superimposed on the overall expansion of the universe, creates complex patterns of galaxy velocities that astronomers have only recently begun to map in detail. The Perseus-Pisces supercluster represents another magnificent example of these cosmic giants, forming a long filamentary structure that extends for nearly 300 million light-years. This supercluster contains the Perseus cluster at one end and includes numerous other clusters and groups arranged along its length like pearls on a cosmic string. The filamentary nature of Perseus-Pisces illustrates how superclusters often form along the dense filaments of the cosmic web, with clusters forming at nodes where filaments intersect. Understanding the formation of superclusters requires us to trace cosmic evolution back to the earliest moments after the Big Bang. The seeds of these vast structures were planted during cosmic inflation when quantum fluctuations were stretched to macroscopic scales. The largest of these fluctuations, encompassing regions that would grow to hundreds of millions of light-years across, had only slightly higher density than average, perhaps 1 part in 100,000. Yet over billions of years, gravity amplified these tiny differences, drawing matter together to create the superclusters we observe today. The growth of superclusters proceeded hierarchically, with smaller structures forming first and gradually assembling into larger ones. Unlike galaxy clusters, which had sufficient density to separate from the cosmic expansion and collapse into bound systems, superclusters formed from lower density perturbations that could slow but not halt the expansion of space within them. This fundamental difference means that while clusters are virialized systems in equilibrium, superclusters are still evolving, with their constituent clusters slowly moving apart as the universe expands. The Coma supercluster, home to the famous Coma cluster, demonstrates the complex structure typical of these systems. This supercluster contains not just the rich Coma cluster, but also numerous smaller clusters and groups, all embedded in a network of filaments populated by more isolated galaxies. The arrangement of these components reveals the underlying dark matter distribution, with galaxies and clusters tracing the densest regions of an invisible cosmic scaffolding that contains most of the supercluster's mass. The discovery of the Laniakea supercluster in 2014 revolutionized our understanding of our cosmic address. This supercluster, whose name means immense heaven in Hawaiian, encompasses the traditional local supercluster as just one lobe of a much larger structure. Laniakea spans 500 million light-years and contains roughly 100,000 galaxies, with a total mass of about 100,000 trillion solar masses. The mapping of Laniakea required new techniques that traced the gravitational flow patterns of galaxies, revealing the boundaries between adjacent superclusters where flows diverge. The Great Attractor, a gravitational anomaly that influences galaxy motions throughout our region of space, lies within Laniakea. This concentration of mass, centered roughly in the direction of the Norma and Centaurus clusters, pulls galaxies toward it from distances of hundreds of millions of light-years. The Great Attractor remained mysterious for decades because it lies behind the plane of our Milky Way, in a region obscured by dust and stars. Only through observations at wavelengths that penetrate this obscuration have astronomers begun to understand its nature as a confluence of several massive clusters and the surrounding overdensity of galaxies. Superclusters are not isolated structures, but connected to each other through the cosmic web. The boundaries between superclusters are not sharp edges, but rather zones where the gravitational influence of one supercluster gives way to another. These boundaries can be defined by surfaces where the gravitational flow diverges, with galaxies on one side flowing toward one supercluster and those on the other side flowing toward a different one. This creates a cosmic watershed, dividing the universe into distinct basins of attraction. The Sloan Great Wall, discovered in the Sloan Digital Sky Survey, stands as one of the largest known structures in the universe, though whether it constitutes a single, coherent structure or a chance alignment of separate superclusters remains debated. This feature extends for more than 1 billion light-years, appearing as a vast wall of galaxies in the survey data. Such enormous structures challenge our understanding of cosmic structure formation, as they approach the scale where the universe should appear homogeneous according to the cosmological principle. The Hercules corona, Borealis Great Wall, identified through gamma-ray burst observations, may be even larger, potentially extending for 10 billion light-years. The existence of such vast structures raises profound questions about the limits of structure formation and the validity of our assumption that the universe is homogeneous on the largest scales. These discoveries push the boundaries of what we consider possible in cosmic structure formation and may require revisions to our models of the early universe. Between superclusters lie vast cosmic voids, regions largely empty of galaxies that can span hundreds of millions of light-years. These voids are not completely empty, but contain far fewer galaxies than the cosmic average, perhaps 10% of the mean density. The few galaxies that do inhabit voids tend to be smaller and more actively forming stars than their counterparts in denser regions, having experienced fewer interactions and mergers over cosmic time. The existence and properties of voids provide crucial tests of our models for structure formation, as they represent regions where initial density was slightly below average. The cosmic web that connects superclusters consists of filaments of galaxies and gas stretching between the dense nodes where clusters form. These filaments, typically a few million light-years thick but hundreds of millions of light-years long, channel matter toward clusters and superclusters. Recent observations have begun to detect the warm-hot intergalactic medium in these filaments, gas at temperatures of hundreds of thousands to millions of degrees, that may contain a significant fraction of the universe's ordinary matter. The dynamics of superclusters are dominated by competing effects of gravitational attraction and cosmic expansion. Within superclusters, gravity slows the expansion, creating regions where the local expansion rate is less than the cosmic average. However, dark energy, the mysterious force driving accelerated cosmic expansion, ensures that superclusters will never collapse into bound structures. Instead, they will gradually disperse as the universe expands, with their constituent clusters becoming increasingly isolated over cosmic time. Computer simulations of the universe on supercluster scales require enormous computational resources, modelling volumes billions of light-years across, while still resolving individual galaxy clusters. These simulations have successfully reproduced the observed cosmic web, including the formation of superclusters, filaments, and voids. The agreement between simulations and observations provides strong support for the lambda CDM model of cosmology, which combines cold dark matter with dark energy in a universe that began with nearly scale-invariant fluctuations. The chemical evolution of superclusters reflects the integrated star formation history of their constituent galaxies. Heavy elements produced by stars are expelled into the intergalactic medium through supernova and galactic winds, enriching the gas in and around galaxies. In the dense environments of superclusters, much of this enriched gas is retained rather than escaping to truly intergalactic space. This creates metallicity gradients on supercluster scales, with higher metal abundances in denser regions where more star formation has occurred. Magnetic fields thread through superclusters, extending from galaxy clusters into the filaments and even into voids. These fields, while extremely weak at typically nano-Gauss strengths, may play important roles in cosmic ray propagation and the evolution of the intergalactic medium. The origin of these cosmic magnetic fields remains uncertain, but they were likely amplified from tiny seed fields through various dynamo processes operating in galaxies and clusters over cosmic time. The future evolution of superclusters will be dominated by dark energy's influence. As the universe continues its accelerated expansion, superclusters will become increasingly isolated from one another. The filaments connecting them will stretch and fade, eventually breaking as the expansion velocity exceeds the escape velocity. In the far future, perhaps 100 billion years from now, each supercluster will become an island universe, isolated from all others beyond the cosmic horizon. Observations of distant superclusters provide glimpses of these structures at earlier cosmic epochs. High redshift superclusters appear less evolved than nearby examples, with their constituent clusters still assembling and their overall structure less defined. These observations allow us to trace the growth of superclusters over cosmic time, providing crucial tests of structure formation models and constraints on cosmological parameters. The study of superclusters has profound implications for fundamental physics and cosmology. The larger structures probe the initial conditions set by inflation and the nature of dark matter and dark energy. They test the limits of the cosmological principle and our assumption of universal homogeneity. Superclusters also serve as laboratories for studying environmental effects on galaxy evolution on the larger scales, revealing how location in the cosmic web influences galactic properties. The future of galaxy clusters. As we peer into the cosmic future, the fate of galaxy clusters becomes intertwined with the ultimate destiny of the universe itself. The discovery of dark energy and the accelerating expansion of the universe has fundamentally altered our understanding of how cosmic structures will evolve over the trillions of years to come. Galaxy clusters, currently the largest bound structures in the universe, will play unique roles in this cosmic future, becoming increasingly isolated islands in an ever-expanding ocean of space. The accelerating expansion driven by dark energy means that the universe will continue to expand at an ever-increasing rate, fundamentally changing the environment in which galaxy clusters exist. Currently, clusters continue to grow by accreting galaxies and gas from their surroundings, fed by cosmic filaments that channel matter from the cosmic web. However, as expansion accelerates, these filaments will stretch and eventually break, cutting off the supply of fresh material to clusters. This cosmic starvation will occur gradually over the next tens of billions of years. Within approximately 100 billion years, the expansion of space will have carried all galaxy clusters beyond each other's cosmic horizons. Each cluster will become causally disconnected from all others, unable to interact with or even observe distant clusters. The observable universe from within any given cluster will shrink to encompass only that cluster itself, creating isolated island universes adrift in an otherwise empty cosmos. This profound isolation represents a fundamental change in the nature of the universe, from the rich, interconnected cosmic web we observe today to a collection of disconnected islands. The internal evolution of galaxy clusters will continue long after they become isolated. Galaxies within clusters will continue their orbital dance, occasionally merging through dynamical friction and gravitational interactions. Over hundreds of billions of years, these mergers will gradually build up the central galaxies of clusters, creating ever more massive elliptical galaxies at cluster centers. The process is slow but inexorable, driven by the fundamental tendency of gravitational systems to evolve towards states of lower energy. The stellar populations within cluster galaxies will age and fade over these immense timescales. Star formation, already suppressed in most cluster galaxies today, will eventually cease entirely as gas supplies are exhausted. The massive hot blue stars that illuminate galaxies today will be the first to disappear, exhausting their nuclear fuel in mere millions of years. Intermediate mass stars, like our Sun, will shine for billions of years before swelling into red giants and then fading as white dwarfs. The smallest red dwarf stars will continue shining the longest, some for more than 10 trillion years. As stars fade and die, galaxies will gradually redden and dim. The brilliant spiral arms and star-forming regions that grace many galaxies will become memories preserved only in the fossil record of ancient stellar populations. Galaxies will become dominated by the faint glow of red dwarfs and the cooling embers of white dwarfs. Eventually, even the red dwarfs will exhaust their fuel, leaving galaxies as collections of stellar remnants. White dwarfs, neutron stars, and black holes orbiting in darkness. The intracluster medium will also evolve dramatically over cosmic time. Currently heated to tens of millions of degrees by gravitational compression and merger shocks, this gas will gradually cool as clusters become isolated and mergers cease. The cooling process will take billions of years, with the gas radiating away its thermal energy through X-ray emission. As the gas cools, it may eventually condense into cluster centers, potentially triggering final episodes of star formation billions of years in the future. Black holes will play increasingly important roles in the far future of galaxy clusters. The supermassive black holes at galaxy centers will gradually grow through accretion and mergers. When galaxies merge, their central black holes will eventually coalesce, creating even more massive black holes and emitting gravitational waves that carry away energy and angular momentum. Over immense timescales, measured in powers of 10 of years, these black holes may eventually consume significant fractions of their host galaxies. The long-term dynamical evolution of clusters will be influenced by gravitational radiation and stellar encounters. Although these effects are negligible on current timescales, over trillions of years they will gradually reshape cluster dynamics. Close encounters between stars can eject them from galaxies, slowly evaporating stellar systems. Gravitational radiation from orbiting galaxies will cause their orbits to decay, albeit extraordinarily slowly, potentially leading to more mergers in the far future. Quantum mechanical effects, utterly negligible today, will become important in the extreme far future. Protons, long thought to be stable, may decay with half-lives of perhaps 10 to the 34th years or longer. If proton decay occurs, all ordinary matter will eventually disintegrate, leaving only leptons and photons. Black holes themselves will evaporate through Hawking radiation, with stellar mass black holes taking 10 to the 67th years to evaporate, and supermassive black holes requiring up to 10 to the 100 years. The concept of the heat death of the universe suggests that galaxy clusters, like all structures, will eventually reach thermodynamic equilibrium. In this state, no further work can be extracted from the system, and all processes that increase entropy will have run to completion. Clusters will become cold, dark collections of stellar remnants and elementary particles with no energy gradients to drive interesting processes. This fate, while perhaps 100 trillion years or more in the future, represents the ultimate endpoint of cluster evolution. However, before this extremely distant future arrives, clusters will experience many intermediate stages of evolution. In the next few billion years, our own local group will merge with the Virgo cluster as cosmic expansion fails to overcome their mutual gravitational attraction. This merger will dramatically reshape our cosmic neighborhood, potentially triggering new star formation as gas clouds collide and transforming the Milky Way and Andromeda into elliptical galaxies. The role of dark energy in determining the future of clusters remains uncertain because we don't fully understand its nature. If dark energy is a cosmological constant, as current observations suggest, the acceleration of cosmic expansion will continue indefinitely. However, if dark energy evolves with time, possibly increasing or decreasing in strength, the future of clusters could be dramatically different. Some models even suggest dark energy could reverse, leading to a big crunch where all clusters eventually merge into a single universe-spanning structure. Advanced civilizations, if they exist within galaxy clusters, might attempt to engineer their cosmic environment to extend the habitability of their clusters. Theoretical proposals include stellar engineering to extend stellar lifetimes, controlled mergers to harvest gravitational energy, or even the manipulation of dark energy itself. While highly speculative, such interventions could alter the natural evolution of clusters, creating artificial structures that persist far longer than natural processes would allow. The information content of galaxy clusters will be preserved even as their physical structures evolve. The distribution of matter, the properties of galaxies, and the history of star formation are all encoded in the present-day structure of clusters. Future observers, even billions of years hence, will be able to read this cosmic history, reconstructing the story of cluster formation and evolution from the fossil evidence preserved in stellar populations and orbital dynamics. The philosophical implications of cluster evolution raise profound questions about the nature of time entropy and the meaning of existence in a universe trending toward heat death. Galaxy clusters, as the largest organized structures, represent the peak of cosmic complexity, arising from simple initial conditions through billions of years of evolution. Their eventual dissolution back into elementary particles represents the universe's journey from low to high entropy, from order to disorder. Near-term observations over the coming decades will refine our understanding of cluster futures by better constraining dark energy and testing our models of cluster evolution. Next-generation telescopes will observe clusters at unprecedented distances, showing us these structures as they were in the early universe. These observations will help us understand how clusters assembled and evolved, providing the data needed to extrapolate their future evolution with greater confidence. The legacy of galaxy clusters extends beyond their physical existence. These structures have served as cosmic laboratories where nature has conducted experiments in physics under extreme conditions. The knowledge gained from studying clusters has advanced our understanding of gravity, thermodynamics, plasma physics, and cosmology. Even after clusters have faded into darkness, the scientific insights they provided will remain as part of the intellectual heritage of any civilizations that arise to study them. Current research on cluster futures focuses on several key questions that remain unresolved. How will the interplay between dark matter and dark energy affect cluster evolution? What role will supermassive black holes play in the long-term evolution of cluster cores? How might quantum effects manifest in the far future of these macroscopic structures? These questions drive ongoing theoretical work and motivate new observations that push the boundaries of our technological capabilities. The computational modelling of cluster futures requires sophisticated simulations that can span enormous ranges in time and scale. These simulations must account for gravity, gas dynamics, star formation, black hole growth, and feedback processes, all while evolving the system over billions or trillions of years. Future improvements in computational power and algorithms will allow even more detailed predictions of how clusters will evolve, potentially revealing unexpected phenomena that emerge only over cosmic timescales. Humanity's discovery and study of galaxy clusters. The human understanding of galaxy clusters represents one of the great intellectual achievements of the 20th and 21st centuries, transforming our conception of the universe from a relatively simple collection of stars to a vast cosmic web of interconnected structures spanning billions of light years. This journey of discovery began with the first telescopic observations of nebulous patches of light and continues today with sophisticated space observatories and massive ground-based telescopes that peer deep into cosmic history. The earliest hints of galaxy clusters came in the 18th century when Charles Messier compiled his famous catalogue of nebulous objects. While searching for comets, Messier documented fuzzy patches of light that didn't move against the background stars. Unknown to him, several of these objects, such as the collection of galaxies in Virgo, were actually distant galaxy clusters. Messier's catalogue, intended merely to help comet hunters avoid confusion, became a treasure map for future astronomers exploring the extragalactic universe. William Herschel and his sister Caroline, working in the late 18th and early 19th centuries, expanded the catalogue of nebulous objects dramatically. William's construction of increasingly powerful telescopes allowed him to resolve some nebulae into individual stars, leading him to correctly hypothesize that some might be distant island universes similar to our own Milky Way. The Herschels catalogued thousands of nebulae, many of which we now know to be galaxies in various clusters, though the true nature of these objects remained mysterious for another century. The great debate about the nature of spiral nebulae reached its climax in 1920 with the famous Shapley-Curtis debate at the National Academy of Sciences. Harlow Shapley argued that spiral nebulae were relatively nearby objects within our own galaxy, while Heber Curtis contended they were independent galaxies at vast distances. This debate highlighted the fundamental uncertainty about the scale of the universe and whether structures existed beyond our own galaxy. Edwin Hubble's observations in the 1920s finally resolved the debate by detecting Cepheid variable stars in the Andromeda Nebula. These stars, whose intrinsic brightness could be determined from their pulsation periods, allowed Hubble to measure the distance to Andromeda, proving it lay far beyond the boundaries of our Milky Way. This discovery expanded the known universe dramatically, revealing that many nebulae were actually entire galaxies comparable to our own. Following Hubble's breakthrough, astronomers began to notice that galaxies were not uniformly distributed across the sky, but showed a tendency to cluster together. The Virgo cluster, the Coma cluster, and other rich concentrations of galaxies became subjects of intense study. Harlow Shapley, despite being wrong about spiral nebulae, made important contributions to mapping the distribution of galaxies, creating some of the first maps showing the clustered nature of galactic distribution. Fritz Zwicky's work in the 1930s on the Coma cluster marked a pivotal moment in cluster research. By applying the virial theorem to measure the cluster's mass from the velocities of its galaxies, Zwicky discovered that the cluster contained far more mass than could be accounted for by visible galaxies. His inference of dunkel Materie, or dark matter, was largely ignored for decades, but eventually became recognized as one of the most important discoveries in cosmology. The development of radio astronomy in the 1940s and 50s opened new windows into galaxy clusters. Radio observations revealed that some clusters contained diffuse radio emission extending far beyond individual galaxies, indicating the presence of relativistic particles and magnetic fields in the intracluster medium. Radio galaxies, with their enormous jets and lobes, were found to be common in clusters, revealing the importance of active galactic nuclei in cluster environments. The launch of X-ray satellites in the 1960s and 70s revolutionized cluster studies by revealing the hot intracluster medium. The Uhuru satellite, launched in 1970, detected X-ray emission from several galaxy clusters, showing that they contained vast atmospheres of gas heated to millions of degrees. This discovery revealed that clusters contained far more ordinary matter in hot gas than in stars, fundamentally changing our understanding of these structures. George Abel's Catalogue of Galaxy Clusters, published in 1958, provided the first systematic survey of rich clusters visible from the Northern Hemisphere. Abel visually inspected photographic plates from the Palomar Observatory Sky Survey, identifying over 2,000 clusters based on galaxy density and richness criteria. This catalogue became the foundation for statistical studies of cluster properties and remains widely used today, with many clusters still referred to by their Abel numbers. The 1980s saw rapid advancement in both observational capabilities and theoretical understanding of clusters. CCD detectors replaced photographic plates, allowing much more precise measurements of galaxy properties. Multi-object spectrographs enabled astronomers to measure redshifts for hundreds of galaxies simultaneously, making it feasible to map the three-dimensional structure of clusters and measure their velocity dispersions accurately. The discovery of gravitational lensing by clusters provided a new tool for studying their mass distributions. The first gravitational lens was discovered in 1979, and by the 1980s astronomers recognized that clusters could act as powerful gravitational lenses, distorting and magnifying background galaxies. This technique allowed direct mapping of cluster mass distributions, including dark matter, independent of assumptions about dynamical equilibrium. The Rosat satellite, operational during the 1990s, conducted the first all-sky survey in X-rays, detecting thousands of galaxy clusters and revealing the ubiquity of hot gas in these systems. Rosat's images show the detailed structure of the intracluster medium, including cooling flows, merger shocks, and the cavities inflated by active galactic nuclei. These observations demonstrated that clusters were dynamically active systems rather than simple relaxed structures. The Hubble Space Telescope, launched in 1990, brought unprecedented resolution to cluster studies. Hubble's images revealed the detailed morphologies of cluster galaxies, the gravitational lensing arcs produced by cluster mass, and the stellar populations of galaxies at various distances. The Hubble Frontier Fields program has used clusters as gravitational telescopes to observe some of the most distant galaxies in the universe, leveraging cluster lensing to extend our view back to when the universe was only a few % of its current age. The Chandra X-ray Observatory and XMM Newton, both launched in 1999, provided revolutionary capabilities for studying the hot gas in clusters. These observatories could spatially resolve the temperature and density structure of the intracluster medium, map the distribution of heavy elements, and detect the subtle features created by active galactic nucleus feedback. Their observations revealed the complex physics of cluster cores and the dramatic effects of cluster mergers. The Sloan Digital Sky Survey, beginning in 2000, mapped millions of galaxies across a large fraction of the sky, revealing the cosmic web in unprecedented detail. This survey detected thousands of galaxy clusters and groups, enabling statistical studies of cluster properties as functions of mass, redshift, and environment. The survey data revealed the large-scale structure of the universe, including vast superclusters and voids, confirming theoretical predictions about cosmic structure formation. The discovery of the accelerating expansion of the universe in 1998, recognized with the Nobel Prize in Physics in 2011, fundamentally changed our understanding of cluster evolution. The existence of dark energy means that clusters will not continue growing indefinitely, but will eventually become isolated as cosmic expansion accelerates. This discovery required revision of models for cluster formation and evolution, incorporating dark energy's effects on structure growth. The Sunyaev-Zeldovich effect, predicted theoretically in 1969, became a powerful tool for cluster detection in the 21st century. This effect, caused by cosmic microwave background photons scattering off hot electrons in clusters, allows detection of clusters independent of their distance. Telescopes like the South Pole Telescope and the Atacama Cosmology Telescope have used this effect to detect hundreds of previously unknown clusters, including some of the most massive and distant clusters known. The Planck satellite, operational from 2009 to 2013, conducted the most precise measurements of the cosmic microwave background while also detecting over 1,000 galaxy clusters through the Sunyaev-Zeldovich effect. Planck's All-Sky survey provided a nearly unbiased census of massive clusters, crucial for using clusters as cosmological probes to constrain dark energy and test theories of gravity. Modern multi-wavelength studies combine observations across the electromagnetic spectrum to build complete pictures of cluster properties. Optical observations reveal galaxy populations and dynamics. X-ray observations probe the hot gas. Radio observations detect relativistic particles and magnetic fields. And infrared observations uncover dust-obscured star formation. This multi-wavelength approach has revealed the complex interplay between different cluster components and the various physical processes shaping cluster evolution. Numerical simulations have become increasingly sophisticated, evolving from simple n-body calculations to complex hydrodynamic simulations that include gas physics, star formation, and feedback processes. The Millennium Simulation and its successors have modelled the formation of cosmic structure in unprecedented detail, producing synthetic universes that can be compared directly with observations. These simulations have been crucial for interpreting observations and understanding the physical processes governing cluster formation and evolution. The discovery of the Bullet cluster and similar merging systems has provided what many consider the most direct evidence for dark matter's existence. The spatial separation between the hot gas and the gravitational mass in these colliding clusters cannot be explained by modified gravity theories, strongly supporting the dark matter paradigm. These systems have become cosmic laboratories for studying dark matter properties and cluster collision dynamics. Recent technological advances continue to push the boundaries of cluster research. The Atacama Large Millimeter Array provides unprecedented resolution at millimeter wavelengths, mapping the Sunyaev-Zeldovich effect in exquisite detail. The Dark Energy Survey has detected thousands of clusters, using them to trace the growth of structure and constrain cosmological parameters. The eRosetta satellite, launched in 2019, is conducting the first all-sky X-ray survey in decades, expected to detect over 100,000 galaxy clusters. Machine learning and artificial intelligence are revolutionizing how astronomers detect and analyze galaxy clusters. Neural networks can identify clusters in imaging surveys more efficiently than traditional methods, while machine learning algorithms can extract physical parameters from complex, multi-dimensional datasets. These computational techniques are essential for handling the vast data volumes produced by modern surveys, enabling discoveries that would be impossible through traditional analysis methods. Citizen science projects have engaged the public in cluster research, with volunteers helping to identify clusters, classify galaxy morphologies, and search for gravitational lenses. Projects like Galaxy Zoo have demonstrated that human pattern recognition abilities complement automated algorithms, leading to discoveries of unusual objects that computers might miss. This public engagement has democratized cluster research while advancing scientific understanding. Current and future facilities promise continued revolution in cluster studies. The James Webb Space Telescope is observing the first galaxy clusters forming in the early universe, revealing how these structures assembled when the cosmos was less than 1 billion years old. The Vera Rubin Observatory will detect millions of galaxies and thousands of clusters, mapping the evolution of structure over most of cosmic history. The Square Kilometre Array will provide unprecedented radio observations of clusters, revealing magnetic fields, cosmic rays, and shock structures in extraordinary detail. The future of cluster research will likely focus on using these structures as precision cosmological tools. Clusters serve as sensitive probes of dark energy, modified gravity, neutrino masses, and the nature of dark matter. As observational uncertainties decrease and theoretical models improve, clusters will provide increasingly stringent tests of fundamental physics. The next decades promise to reveal whether our current cosmological model is correct or whether new physics awaits discovery in the largest structures of the universe.